Alright class, in this video we're going to talk about the scalar and vector projections of one vector onto another. And the concept is pretty simple. So if we projecting u onto v, so let me write that down, u onto v, what do? Well, the concept is that we go to the end of u and we drop a perpendicular down and we have a vector right there. Okay? So the vector is the vector projection, and that's of u onto v. The length is the scalar projection. Now let me just say, there's not a whole lot of uses for the vector projection, but we'll talk at least about one of them. The scalar projection is very important in finding distances. Okay, so let's derive how we get it first. So first of all, we let theta be the angle between u and v. So we have this familiar picture that we've seen before. Okay, and we drop this down, and we're looking for this vector right here. Okay, or that distance. Let's say the distance first. Okay, so I'm going to call that distance x. And in terms of this right triangle, if we take the magnitude of u, so let me just do that right quick. So magnitude of u there. This is going to be involving x and magnitude of u. That's going to be cosine. Okay, so cosine of theta equals x over the magnitude of u, where x is that distance that I'm trying to find. So let me just flip this around. X is going to be cosine of theta times the magnitude of u. And using our cosine formula we developed the other day, we can say that this is u dot v over magnitude of u times magnitude of v, and then times another magnitude of u. So those u magnitudes cancel, and we get, this is what we're going to call it, we get the scalar projection we get that that's equal to, we're going to say comp, meaning the component of u in the direction of v. So component of means the distance, and that's going to be u dot v over magnitude of v. Okay, so first thing we should note, this could be negative. And that's because dot product can be negative. And what would the picture look like there? The picture would look like this. So you would actually be going, so the angle would actually be an obtuse angle. So when you do the projection, you're projecting back this way and it's going in the opposite direction of v. Okay? We're going to be using this a lot to find distances, and we'll do that later. But what we want to note is when we calculate distance, we're going to take an absolute value. Okay, and that way it'll be positive. Okay, the vector projection. Okay, there's a reason why we talk about this one second, and that's because you have to get the scalar projection before you can do the vector projection. So we're going to say that this is the projection of u onto v, so proj of u onto v, and that's really, really simple. It's the length that we just calculated. So u dot v over magnitude of v, and that's going to be multiplied times a unit vector in the direction of v. So remember, this is how we find the unit vector in the direction of v. So let me write that down. Okay, so remember how we do that? We just take v and we divide it by its magnitude. So that's a scalar. The denominator there is a scalar, but v is the actual vector we're given. Okay? And what's the use of this? Well, that's a good question. At least I can tell you what physicists usually use it for. So I can represent, if I have a vector u and a vector v here, okay, so I can actually represent u in terms of a vector that's parallel and a vector that's perpendicular to v. So a linear combination of these. So this vector here would be the parallel vector, and this vector here would be the perpendicular vector. And the relationship we get is that u is v parallel plus v perpendicular. Okay? And that comes in handy when you want to break things into components in terms of another vector. The way you calculate these, so it's actually really easy. So v parallel, that's just a vector projection of u onto v. And then looking at what we have up here, if we solve for v perpendicular, we would know u and we would know v parallel at that point. So v perpendicular is u minus v parallel. And then you would just do that with your standard vector addition. Okay, that's it.